protocol is a set of rules and message formats. We have different protocols for data communications. We group protocols based upon the task that they need to achieve. And in the TCP/IP protocol architecture, we have 5 layers or 5 groups of protocols. They perform different jobs. The physical layer protocols are about getting bits or getting the raw data across links as some signal. So the protocols about within the physical layer, how do you transmit a signal? What type of signal? Data link layer is about getting the bits efficiently and accurately across a link, across a single link. Network layer protocols are about getting the data from one point to another point on a network. Not just one link, but when we have many links, like a link or a network across the globe. How do we get the data from my computer to a server in the US? That's the role of the network layer protocols. Transport layer is about supporting applications. Applications often need reliable delivery of data. Transport protocols often support that and making sure that if I send data across the internet and somewhere in the middle there's an error, something goes wrong, then a transport protocol like TCP will try and fix that error. And the basic way it does it is says we send some data. If the receiver detects there are some errors with what it received, it tells the sender to send again, to retransmit. So transport protocols are about getting data between applications. And then we have protocols specific to individual applications. So a protocol that supports web browsing, a different one that supports email, another one that supports different applications. So a protocol architecture classifies protocols based upon the tasks that they're built for and divides it into layers. What we're going to do in our example, and it's going to take most of this lecture, we'll go through a real example and we'll try and demonstrate the layering and how data flows through the layers. The example I'm going to use is the most common one that you know, the most common internet application you know is web browsing. What I'm going to do is open my web browser, visit a website, and then something will be displayed on my web browser. And then we're going to inspect in detail what actually happened for that communication to work. We're going to look at what happened within the different layers. So to do that, I need to access some website. Let's draw a picture. We don't need the Higgs boson. In fact, you don't need to draw this. One of the later slides has something similar. But with web browsing, we have a server, a web server, and a browser. If this is a computer, we have a browser application and a server application on another computer. And I send a request to the server for some page. The server sends back a response containing that page, if all goes well. I think on slide 26 or 27, and we'll jump to it in a moment, you have what we're going to go through. For this demo, the browser is my laptop, or the browser is running on my laptop, and the web server is running on the IT server. It's a PC down on the 3rd floor. It's just in the computer center somewhere in the SIT network. That is, in my browser, I'm going to access I'm going to type in some URL, and it's going to show something on the browser. Then we're going to see how that worked. This is me accessing the IT server, it.sittuacth/index.html. Here's the page. I'm going to create a new page just for this demo. So first thing to set up this example, I'm going to connect remote log in to the IT server. You did this, some of you did this to get your passwords. some of you use Windows and PuTTY or PuTTY to connect. I'm using Linux, and I'll just do it on the terminal. We use a protocol called SSH to connect to another computer. I need to supply my password. Gives some long warning. And now, everything that I type in is not running on my laptop, it's running on the IT server downstairs. Okay, that's what we mean by a remote connection or a remote login. Everything I type now is running on a different computer. This is the IT server that you have and use for Moodle. It has a web server running on it already, and how the web server works is that in some specific directory, this /var/www directory, all the files in that directory are made available by the web server. I'm going to change into that directory, cd, and then list the files. You'll see them here. The index.html file. That file contains the page that you see when you visit the home page of an IT server. The Moodle directory contains all the pages related to the Moodle website. And there are some others. The instructions for how you logged on with Windows are in this file, and there's some pictures there and so on. So all of these files are available via the IT web server. I want to create a new web page for just this demo, and it's called it.html. I can do this because I'm the administrator of this server. You cannot, or you do not have permissions to do this. Nano is just a text editor, and I'm going to create a new file. And it's just some very basic HTML I'm creating, just for this example. Everyone knows how to create HTML. You either have done it or you'll be doing it in Dr. Tanarak's database project, I expect. But maybe you'll use a different editor. So this is the web page that I'm going to access in my example. Okay? Just some HTML. We'll see it shortly come up. You see the file now exists. This it.html is now on the server. Okay. I'll exit from the server. I no longer need it. Clear my screen. I'm back running on the laptop. What I'm going to do is from my web browser on my laptop, type in that address, which will be SITTUACTH/it.html. This domain name identifies the server, the computer. This identifies the file that I want to access. So I'm going to type that into my web browser address bar. And then to see how data communications work and how the protocols across the layers work, what I want to do is see what exactly does my computer send. I want to see what does my computer send out onto the network and what does it receive back. And from seeing that, we'll be able to understand the relationship between layers. To see that, I need to run some special software on my laptop. Okay? Software that captures all of the packets that my computer sends and receives. So I need to start that special software first. The software I'm using is called TCP dump. I'm going to use, my laptop is connected to the Wi-Fi network. So I'm going to use my wireless LAN part of the laptop, and I want to capture everything using my wireless LAN, or everything that my wireless LAN, identified by WLAN 0 on my laptop, everything that it sends and receives. minus n is an option that we're not going to explain. I want to capture everything that it sends up to a size of 1,500 bytes. And everything that I capture, I want to save into a file or write to a file called itcapture.cap. This is just some special software, TCP dump, that records everything that my computer sends and receives. You can run similar software, and we'll show you later the name of that software. I need my password. And it's running. This software is listening on my wireless LAN interface, or my wireless LAN card. By listening, it means everything that my wireless LAN sends and receives, it's recording. And it's recording into this file. We cannot see anything here, but it's actually running. We'll see later what it records. So now I'm recording everything that I'm sending and receiving. Let's access the website. So the web server has the page. In my web browser, it's not index.html, but it.html. Okay? And let's see what happens. Okay, I pressed enter, and the web page that I created is now displayed on my browser. So on my browser, I typed in the URL, pressed enter, and within half a second or so, the browser showed the page which was sent from the server. We'll see shortly that what happened is that my browser sent a request to the server for the page, and the server sent back the page to my browser. And then the browser took the HTML and displayed it on the screen. Now go back to my capture, because that's going to show me what actually was sent, what packets were sent by my computer. I'll stop that, Control C. During that time, that software recorded or captured 2,331 packets. Only some of them are going to be related to accessing that website. So the file now contains all those packets. To look at them, actually before we look at them, I need some other information. Everyone knows what an IP address is. An internet address, an IP address, most likely you deal when you connect to the Wi-Fi SIT, you probably know, or sometimes you see, you get an IP address. When you connect in Windows, you see something flashing down the bottom, means it's obtaining an IP address. We'll discuss them shortly, but for this example, I need to know my laptop's IP address. And I can use ifconfig, which we'll explain later to get that. Let's just record it. My laptop's IP address is 10.10.99.251. So I've captured these packets. Now we want to look at them. And the program we can use to look at them is called Wireshark. And in fact, this is the program you can use at home or on your computer to capture the packets. You don't have to do what I did. You don't have to type in a strange command like this. On Windows, on Mac, on Linux, you can download Wireshark for free, install it, and it will capture for you. You just click on some buttons and it will record everything that you send and receive. This morning when I did this example, it didn't work. Let's see. Or it didn't work 100%. We'll go through this and explain what we see. So Wireshark, in this case, is presenting to me a list of packets that were captured. There are three parts in Wireshark: the top frame, then the middle, and then the bottom. The top lists the packets, packet number 1, 2, 3, 15, and if we scroll down we see there's 2,000 or 3,000 packets. And for each packet it gives some summary information. We'll explain in a moment. When we select the packet, the orange part, or the details of that individual packet are shown here. Turns out everything that we send through our computer is just binary, just bits. So Wireshark is presenting in some nice format that we can read and understand, but it's all just zeros and ones. This pane shows the raw form of the packet being sent. Fortunately, not in binary. To make it a little bit easier, it's in hexadecimal. Okay? Of course, you can convert the hexadecimal to binary. I'll zoom in a moment and explain a bit more. But we've got 2,000 packets here. Many of them I know in advance are not related to my web browsing. They're related to other things happening in the background on my laptop. Okay? So what I'm going to do is filter out all the packets that are not relevant. I don't want to show them because it becomes too complex. I'm going to filter and show only the packets that came from and to my IP address. So add a filter here where my IP address is 10.10.99.251. Enter. And that removes some of the packets. But there's still a lot here. Some of them I don't want to have to explain right now. They're not related to what we just did. What application protocol did I use when I accessed the web server? What application protocol did I use? TC? No, I used TCP dump is an application to record packets. But when I opened my browser and typed in a URL and pressed enter, what application protocol did my browser use to access the web page from the server? HTTP. We see it, or you don't see it in the browser nowadays, but you know the start of the URL is in fact 2 slashes, HTTP. HTTP, the hypertext transfer protocol, is used for transferring HTML, hypertext, from a server to a browser. That's the protocol I used. Let's record that. That's the application layer protocol used by my application. So there are many things shown in this capture. I just want the HTTP packets. So I'll filter based on that. Okay, that's easier. We just have 2 packets now to look at. So my laptop over that minute or so sent 2,000 packets. 2 of them, just 2 of them, these 2, used HTTP and were to and from my laptop. The others we don't want to worry about at this stage. Let's look at those 2 in detail. And let's zoom in to do so. So we have 2 packets. What this Wireshark software shows us is the details of those 2 packets. I think it's on slide 26. Slide 26, you see an example of web browsing using HTTP. It shows the exchange. It shows the basic way in which HTTP works. Maybe we should go to it. I should go to it. We'll come back to the things we've skipped later. My web browser running on the laptop, the web server, which is just some software running on another computer. The way HTTP works is that using HTTP, the Hypertext Transfer Protocol, the web browser, or first at point 1, the user types in the address. I typed in the address, or you click on a link. Either way. I typed in address, I press enter. HTTP creates, or the web browser creates some request to send to the server. And the structure of that request, it's a string. And it contains many things, but the main thing we care about is it contains some string saying get and the file name we request. I didn't get test/index.html. What did I do? If this is my web browser, after I typed in the address and pressed enter, the web browser goes to work. It creates a request, and HTTP formats that request as some string, which is get. In my case, it will be it.html. There may be some things after it as well. It's really saying to the server, I want to get this file. Okay? And my server running on another computer is going to receive a message containing this get request. What the server does at point 2 is checks, does that file exist on my server? And remember, when I created the file on the server, I created it in some directory. If it exists, and it will in our case, and everything's okay, the server sends back a response. And the response contains some status code, and importantly, the response contains the contents of the file that was requested. So the contents of my it.html file that I created should be contained in the response. I'll just write response here. That's the basics of HTTP. There are many other features, but the most common one that we use is we send a GET request to the server sends back a response containing the file that we wanted to get. Let's see that in our packet capture. In fact, we see those two packets in the top pane, the orange one and the one below it, the green one. Packet number 1110 is the GET request. What Wireshark does is it summarizes information about that one packet. The one packet that was sent by my computer, it was sent at time 41 seconds after I started the capture. It was sent by some computer with source address 10.10.99.251, i.e. my laptop, and it was sent to some computer with IP address 203.131.209.72. And you can guess that that's the IT server. We will talk a bit more about addresses later, and we don't need to know the structure, what these numbers actually mean. You just need to know that this is some address of a computer in the internet. This is the address of the IT server. This is the address of my laptop. This packet was captured by my laptop, sent from my laptop to the IT server using HTTP. And a summary information that that packet contained is that it's a GET request asking for /it.html. The other bit at the end is just the version of the protocol being used, 1.1. Then, what's this? This is 44, what's the units? How long later did the response come back to my computer? My request was sent at time 41 seconds, 0.802453. The response was received at 41.846281. How many milliseconds? How many milliseconds approximately between, here's my laptop running the browser, The first message is when is the request being sent. Then sometime later I receive a response. What's the time? How many milliseconds? 41 is in seconds. How many milliseconds? About. Can anyone subtract one number from another? Milliseconds. Milli, remember, is 10 to the power of minus 3. So we have seconds, and below that milliseconds, then microseconds. So 10 to the power of minus 3. This is 41 seconds, 802 milliseconds. This is 41 seconds, 846 milliseconds, if we ignore the last 3 digits. 46 minus 2, about 44 milliseconds. That is, from my computer sent a request, and 44 milliseconds later, it received the response, and then displayed that on the web page, on the browser. Okay, about 44. What Wireshark shows us for each of those packets, we've currently selected this orange one, the first one. In this frame, or this window, it shows us the details of that packet. And we'll go through those details. It shows us the layered, or the protocols used at each layer to communicate. It's in fact the opposite order from what we think of or we draw our stack, but we'll overcome that quite easily. Let's try and draw it here. We can remember this information, we don't need that. So we're going to go through how does the data from the application pass through a protocol architecture or a protocol stack inside my computer. Let's draw this somehow. I'm drawing this rectangle to represent the piece of data created by the web browser. Let's call it the GET request. That is this message. That represents the string that's being sent from the browser to the server. That's created by the application layer protocol, HTTP. So what happened at the start? I typed in the URL, pressed enter. My Firefox web browser goes to work. It calls, or it uses or implements HTTP, and it creates a string which we'll call the GET request. That's the first piece of data. We want to send that to the web server. What does it look like in detail? We can look at the detail here in Wireshark. I can expand that. We see it has this string get/it.html and the version of the protocol being used. It has some other optional information as well. It has the name of the server computer. It has some string identifying my web browser. It's Mozilla Firefox running on Linux. So it's something that identifies the web browser that's sending this request. Something about the language that my web browser prefers. I send a request for a page. Maybe the server has that page in multiple languages. So my browser tells the server, please, I prefer to receive it in English. The server could compress the file if it wanted to. You don't need to know these. We're just giving an example of this is the actual information sent from my browser to the server. Importantly, it's a GET request for some file. That's this, or that's what's inside here. That's done by the application, Firefox in my case. And then the application, specifically HTTP, the application layer protocol, sends that data to the next layer to process. So we'll draw it sends all of that down to the next layer, and the next layer uses a different protocol. What protocol? What does the transport layer use in this example? You can see it on the screen. You may not see it in your handouts. TCP, where do we see it? I'll just minimize this again. The way that Wireshark presents it is in the opposite order. This is the application layer protocol, the top level, then the next level, then the next, and so on. So HTTP, the transport protocol that it sends it to, is TCP. And we'll see the third one, the next one, is IP. And then we'll see is Ethernet. We'll get to them in a moment. So in this instance, my web browser is using this set of protocols. Application, HTTP, we create a GET request, we send that to TCP. TCP is just a piece of software running in your operating system. So we could classify, all right, the GET request was done by Firefox, an application that implements HTTP. TCP and IP will see are normally part of your operating system, just some software running in your OS. When you install Windows, it includes TCP and IP and other protocols. So this is all communications inside my computer, nothing being sent out yet, just inside the computer. The GET request is sent to TCP. TCP does some processing. It's a protocol, it follows some rules. One thing that it does, if we select it, it adds some extra information. And the way that I'll draw it, this is the original data, and this is the TCP extra information. We'll call it a header. That is, we add some extra information to the head of the data from the upper layer. What is this information? What is in the header? All of this stuff. We don't need to know what it is. It includes some source and destination address. They are really numbers that represent the applications that are communicating. But we won't go and explain any of these. They are needed for TCP to work. TCP does some processing, follows its rules, and adds the TCP header, and eventually sends all of that down to the next layer. Still inside my computer, and specifically inside the operating system. And the next layer is IP. So now we're down to the network layer. The Internet Protocol receives this sequence of bits from TCP, does some processing, whatever it needs to do, adds a header. The header contains these fields, this information. Two things we recognise, well, several things in fact. Right? It contains the version of the protocol being used. The most common version of IP that we use today is IP version 4. There's a newer version, version 6. We're focusing on version 4 for this course. It indicates how long is this header. This is 20 bytes. How long is the entire packet so far, 353 bytes. And two things we recognise here: who sent this, who is the source, and where is it going to. The source address and destination address are included in the IP header. Remember, my laptop has the source IP address of 10.10.99.251. And you'll have to trust me in that the destination, the IP address of the IT server is 203.131.209.72. So this IP packet contains the address of my laptop, who is sending the packet, and the address of the server, who I want it to reach on the internet. What's next? Next, IP does the processing, passes it down to the next layer. In this case, Ethernet. This diagram I'm drawing is the same as on slide 27. You have it in front of you. Ethernet is a protocol. This is at the data link layer, and that does some processing. We don't know what yet. We haven't studied that in enough depth, and adds a header. The diagram on slide 27 shows something else. On slide 27 you'll see you can sometimes add stuff to the end of the packet, not just at the start. I'm not sure if it did in this case, but it's possible. This is the original data. We add some control information to the start and optionally the end of the packet. The start is called the header, the end is called the trailer. Some protocols differ in how they do it. Ethernet, I think, in most cases adds a trailer as well. It's not shown on Wireshark. It's just extra information needed for Ethernet to work, the Ethernet protocol. What's next? We're using TCP IP, using HTTP for our web application. What technology did my laptop use to send this message? Anyone want to guess? Hint, I did not plug in the cable when I sent it. Wireless, what would you call the technology? Or what some names you know it by? The wireless what? What do you... Wi-Fi, wireless LAN, not WiMAX. Different names. One common name may be Wi-Fi. The general name is wireless LAN. The name of the standard is, and you may have seen this on products, is IEEE 802.11. So that's wireless LAN access via your laptop is using this. This is all the same meaning, the same technology. Wireless LAN, Wi-Fi 802.11 is the name of the standard. So my laptop is using wireless LAN. But Wireshark reports Ethernet as the data link layer. The only reason here is that, in fact, wireless LAN, using wireless access from my laptop, the standard or the protocol uses the same format of messages as using the wired LAN. Ethernet is the name of the wired LAN protocol. When I plug in the cable, I'm using Ethernet to communicate. When I'm using wireless, it's called Wi-Fi or wireless LAN, but in fact, it's very similar to Ethernet. And that's why here, Wireshark says this packet is using Ethernet. I'll just make a note. We in fact know it's using Wi-Fi. That is, my laptop is using Wi-Fi at the data link layer. And that's it in terms of what we captured. The next thing, the frame part here, just summarizes the entire, all of this. It says, in total, we have, what? 367 bytes. That's, if we add the original data, the GET request, plus all these headers and the trailer, totals 367 bytes. That's what was sent by my wireless LAN card. In fact, we don't see what the physical layer does. The physical layer is normally inside the hardware. And Wireshark, this program that, and the TCP dump that captured, cannot see what the hardware does. It only sees what the software does on your computer. So it only sees up to here. What happens next is that, although it's not shown in Wireshark, is that this is sent to the physical layer, and the same, or it's the name is the same, Ethernet or Wi-Fi. Wi-Fi, in fact, has its own data link layer protocol as well as a different physical layer protocol. It operates at both. We'll come back to that in a moment. This is at the data link layer. It's sent to the physical layer protocol for Wi-Fi. And the way to think of what the physical layer does is it treats this as a sequence of zeros and ones, bits. And it somehow converts those bits into some signal to send. The way that it converts bits into a signal is part of the protocol. We won't discuss that yet. But the physical layer takes the bits, creates some signal, and transmits the signal out of my laptop, some radio signal in this case. If I was using the cable, it would transmit some electrical signal across the copper wires. So that's the physical layer. Although it's not shown in Wireshark, we can visualize as converting to some signal. And that's sent up to the access point and then eventually down to the IT server. So what we're doing in this example is seeing how the data flows through the protocol layers. It flows through the stack. Inside one device, it started out as a GET request. Each of the protocols do their processing, add some extra information. Eventually, it's all transmitted as a signal, goes across the air, and if we draw it, here's my laptop. If we draw the network, here's the access point on the wall. I send from the laptop to the access point. The access point has a cable going to some other device, somewhere on another floor. Maybe some other device. We don't know, not from the information we have here. And eventually, it connects into the IT server, where the laptop has an IP address, and the IT server has an IP address, whatever it is. 131, 203, 131, 209, 72. That's an example of our network in this case. I don't really know what's in here. It's a little bit more complex than this in SIT, but we know, well, I can see at least, the laptop sends the access point. I know the access point's connected to something else, and we know that the destination is the IT server. We know the IP address of the source and destination. So our signal comes out of the laptop. It goes through the air, it goes up to the access point on the wall. It arrives at the access point, and the access point then processes the signal and then looks at the data that it represents and does some processing and then sends it on as some signal to the next device, which processes it and then sends it on to the next device and then on to eventually the IT server. So we can think the IT server receives some signal. I won't draw it again, but look at this diagram in the opposite direction now. We receive some signal at the IT server. The physical layer receives some signal at the IT server. It may not be Wi-Fi, it may be something else. It sends the bits that that signal represents up to the data link layer, the next higher layer. So what we get at the data link layer at the IT server now is this Ethernet packet. The data link layer processes, removes the header and the trailer, leaving us just with this part. Sends it up to the network layer inside the IT server. IP processes it, removes the header, sends this part to the transport layer. TCP processes what it receives, eventually removes the header, sends this up to the application layer in the IT server. So what's received at the application layer in the IT server is this GET request. Maybe we can draw it, at least the top part. The IT server, if I draw it quickly, some signals received. We have the Ethernet header and trailer processed by the data link layer. That's sent up. The contents of it is sent up to the network layer, which contains the IP header. The contents of that is sent up to TCP, the transport layer. And then the contents of that, which contains the TCP header, is sent up to the application layer. And what's left is the GET request. The original thing that came from the laptop, this piece of data. So that's the process of delivering the data from one application on one computer to an application on another computer, through the layers within each of those computers. The goal is to get the request from here to the IT server. It's been achieved. Many things or details we've skipped over, but we'll just try and concentrate on the things we need for now. What happens now? What's next? The server application has received a GET request. What happens next? Who sends what back? Server sends back the web server receives a request for, and it's up here, the file it.html. If it exists, and we know it does because I created it at the start of the lecture, it sends back a response, which is the second packet here. It's the response coming from 203.131, the IT server, to my laptop. We see it has the same structure. It has HTTP, TCP, IP, Ethernet. So that's received coming from the server back, following the same layered approach. And eventually my laptop receives the response. That is, it receives a signal from the access point. It passes to the data link layer. The data link layer removes the Ethernet headers. The IP removes, and eventually what's received is what the server sent And in Wireshark, it shows us here this line-based text data. That's the original data sent by the server. What is it? It's the web page. It's shown here. You can see it's the HTML that I created in the web page. So this second message is the response. So packet number 1112 is the response from the server to the browser. The original data contained in that is the web page, which is to be then displayed on the browser. And we see on the browser the message, hello to the class. What have we missed? What have we missed? Any problems? Any things you don't know? When you do the quiz 3 this afternoon, you'll be able to answer what happens in the flow of data. Quiz 2 was open yesterday. Quiz 3 has started today. Any questions on how... We're not focusing on the individual protocols and how they work. We're focusing on how the data flows through the stack. Any questions? So I say TCP does some processing. What does it do? Well, it does a lot of things, but we don't cover that until after the midterm, what it does. Why does it add certain things in the header? Again, we won't cover that until we go into detail of TCP. We're just mentioning that it does add some header and passes it down to the next layer, and so on. And when we receive, we go up through the stack. How long is an IP address? How long is an IP address? Let's find out. We'll cover, when we go back to the slides, we'll look at IP addresses. Wireshark, and I recommend you use it, download and install Wireshark on your own computer, because you can see and find out many details of what's happening when you access some network. You can do other things as well, diagnose problems. You can see what data is being sent by your computer. Maybe you have a virus running on your computer. Then you'll be able to capture and see if that's sending anything out that you don't want to be sent out, although that could be difficult. One thing it shows us, everything I draw here is just bits. Okay? The data, although it was a string, we could use ASCII to convert that to binary. When we add a header, again, they're just binary values. It's just that we normally show that in decimal or in some other easy to read format. But it's all just bits sent through the computer. Wireshark shows us the hexadecimal values. When I click on this source address, the source address 203.131.209.72 in hexadecimal is CB83D148. How many bits? How many bits is an IP address? How many bits do you need to represent one hexadecimal digit? 4 bits for one hexadecimal digit. Remember, hexadecimal goes from 0 to 15. If you have 4 bits, we can represent all 16 values. So one hexadecimal, 4 bits. The IP address has 8 hexadecimal digits. It's 32 bits in length. An IP version 4 address is always 32 bits in length. We'll see that shortly later. And we can see, oh no, that's enough on Wireshark. Any questions before I shut this down and we return to our slides? What you should gain from this example is the knowledge of how data flows through the stack, how protocols run at each layer. The protocols process the data according to their rules and optionally add headers and trailers and then send to the next layer to process and the next layer. And it's only the bottom layer, the physical layer, that actually sends something across a network. It's only the physical layer that transmits something out of my computer or receives something into my computer. The rest is done by applications, the operating system, and hardware. Say the LAN card or the wireless LAN chip inside my computer. But all of this is inside my computer. Let's go back to the slides and see what we've missed and summarise. Actually, so we know how HTTP works, the very basics. Send a GET request, server sends back the page that you requested. But in fact, to get that to deliver the GET request from source to destination, many other protocols are being used as well. TCP, IP, Ethernet. If we go back, oh actually this is the one that I've just drawn here. I'll go back. What have we missed? We know our layered stack. You know that. You need to learn what does each layer do. What's the responsibility of each layer in general terms? We drew what happened at my laptop, and it's similar at the IT server, the destination computer. They have the same set of protocols. But not every device in a network has to implement all layers in the stack. Here's an example where we have 3 devices: a source host, like my laptop, a destination host, like the IT server, and connected via 2 cables via some intermediate device. It's called a router here, but we have some intermediate network device connecting them. These are the links, say the cables. Importantly, the physical layer and data link layer are common across each link. What this diagram shows is that from the source host to the router, across this link, the physical layer must be the same at each of them. They use the same protocol. If 2 entities want to communicate, they must use the same protocol. You can think they use the same language. They talk the same language. Same at the data link layer. The router and source hosts use the same protocol at the data link layer. But across this second link, they must use the same here and here. The data link physical layer used here does not have to be the same as here. This may be Wi-Fi, this may be some optical fiber technology. So the different links may use different physical and data link layers, but across the same link on either endpoint, they are the same. This physical layer protocol must be the same as this one. That's what the blue line showed. They must be able to talk to each other, that is, speak the same language. Across a network, at least for a router and these hosts, they all talk the same network layer protocol. For example, they all use IP. From end to end, at the transport and application layers, both the hosts must talk to the same protocol. That is, in our example, the laptop and the IT server use TCP and HTTP. But note, the intermediate devices aren't evolved in the application protocol. The switch, the router, the access point, they don't know that it's HTTP. They don't care. All they know that it's some data being sent from someone else to someone else. So the intermediate devices do not always, or do not take part in the application or transport protocol. They are just at the endpoints. Let's spend 2 or 3 minutes talking about standards and then finish with an example. This just describes those layers. We've mentioned them several times. We're focusing this course on TCP/IP protocol architecture. There are others. In the past, there was an OSI 7-layer architecture. It's no longer commonly in use. It's only in very old networks. There were older architectures. IBM had one. Apple had their own architecture. Rather than using TCP/IP in Apple's network, they had their own set of protocols. Novell had theirs. Again, these are no longer in widespread use. Only, mostly have been replaced by TCP/IP. There are some architectures that are specific to domains, especially telecommunications. That is, your mobile phone. You have a GSM mobile phone. It uses a stack of protocols different to TCP/IP. So within mobile phone technologies, there are different protocols used. But the most widespread one today is TCP/IP, and that's what we focus on in this course. A protocol we know is rules for communicating entities to follow, implemented in applications, operating systems, software or hardware. A standard are protocols that some organisations have agreed to follow. You go and design your own protocol. That's fine, you can use it on your computers, but you want everyone in the world to use it. Well, the most likely way to get others to use it is a set of organisations who are going to most likely use it agree to use your protocol. They create a standard. So it's gone. IEEE 802.11 is a standard for wireless communications. GSM is a standard for mobile phone telecommunications. So a standard defines a set of protocols which is agreed upon by different organisations. I may give you some more examples of standards through the course. And you'll definitely see some references to these organisations. There are different organisations that create standards. ISO, ITU, IEEE, IETF, W3C. ISO creates many different standards from data communications to management and services. ITU, mainly about telecoms. IEEE, electrical engineering, electronics. IEEE 802.11, wireless LAN, Wi-Fi. IETF creates internet-based standards. IP, TCP, created by IETF. W3C, HTML, XML, those web-based technologies. And there are others. Just be aware of some of them. What I want to finish on is an example of addresses. We saw already that my computer has an IP address. Remember yesterday I had those LAN cards, and they had chips on them, and you plug the cable into the socket. We call that a network interface. It's the interface for my device to attach to a network. How many network interfaces does my laptop have, do you think? 3. What are they? Name them. How many? LAN. So the wired LAN is one network interface. I can plug a wired LAN into my laptop. There's one. What else? Wireless LAN, Wi-Fi. 2. Anything else? Bluetooth would be another one. And in fact, that's all my laptop has. Some may have a 3G chip inside. Your mobile phone most likely has those 3. Some may have infrared, some may have NFC. These are the technology to connect to different networks. We call each one a network interface. Each network interface has an address associated with it. On my computer, I can see the addresses of my interfaces using IF for interface config. I have to scroll up. My Bluetooth is disabled on my laptop. Even though it's there, it's turned off, so it doesn't show up in my operating system. This shows on my computer, all right, this is ETH0, LO, WLAN 0. LO is a special case for my computer. Ignore it. There are 2 interfaces relevant to us. The wired Ethernet interface and the wireless LAN, the Wi-Fi interface. Both of them have an address, referred to here as a hardware address. The hardware address of my wired LAN interface is this 12-digit hexadecimal value, 00 through to EC. 12 hexadecimal digits. How many bits? How many bits? 12 hexadecimal digits. Use your phone to calculate. Or calculate in your head. 12 hexadecimal digits. How many bits? 12 hexadecimal digits. How many bits? 48. Remember, 1 hexadecimal digit, 4 bits, 0 to 15. It's a 48-bit address. My wireless LAN also has a hardware address. This is the address of the network interface, the hardware part of it. Almost every interface will have its own hardware address, and they're different. That is, they're different values, you see. When we want to use the internet and attach to some network, we may also obtain an IP address or internet address. My wireless LAN interface has an IP address or INET address here, 10.10.99.251. My wired LAN interface doesn't have IP address. There's no cable plugged in. Normally an IP address is obtained automatically or dynamically, whereas a hardware address is normally programmed into the hardware. When I buy the laptop, it comes with this hardware address. I cannot change it in hardware. I can pretend to be different, but that is assigned to the hardware. So devices, we can think have a hardware address, and when we attach to the internet, we also get a network or logical address, specifically an IP address, an internet address. Your homework for the next week, 3 things. Find the addresses of your computers, your phone, your laptop, your home PC if you have one. Find the addresses, both hardware and network or IP addresses. Find out how to find them and find out their values. There's 1. Homework number 2, do quiz 2. Homework number 3, do quiz 3. You have three tasks, okay? Quiz 2 is due Monday. Quiz 3 is due Wednesday, I think. Very short quizzes would take you 5 to 10 minutes to do them.